Hello viewers, we are looking at ordinary, we're still on ordinary differential equation, and under ordinary differential equation we are going to be considering exact equation. And so we've done something on separation of variable, we've done homogeneous equation, we've done the use of integrating factor, we've done direct integration, and so we are looking at exact equation. Because there are equations that you cannot use direct method to solve direct integration. There are equations that, from the beginning you cannot solve using by separating the variables, or equations you cannot solve because you cannot solve this one using homogeneous equation, because the power of x is of a higher value than the power of y. And so this is an exact equation. And how do you know it is an exact equation? Exact equation, if you have m dx plus n dy equal to 0, this is a very important formula you have to take note of when you are looking at an exact equation. And then for you to say that the equation is exact before you can solve, because before you solve an exact equation you have to test to find out if the equation is exact. You have to test to find out if the equation is exact. It is after testing that you know, okay, yes, it is actually exact equation before you can solve. But there are cases that you test for the exactness of the equation and it is not exact. There is a method to solve that one, which is you have to use a method of integrating factor, and then you convert it using method of integrating factor to exact equation before you solve. But I think this one is going to be exact, and then we'll solve it. I'll also make a video on the question like this that is not exact, where I'll have to use the method of integrating factor to convert it to exact equation before solving. So let's look at this. So the two basic formula you have to take into consideration when you are solving exact equation is, first, m dx plus n dy will be equal to 0. And for you to say it is an exact equation, it means that the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. So if you have the partial derivative of m with respect to y having the same value as the partial derivative of n with respect to x, you can say that the equation is exact. So it is at this point that you can now solve it. Okay, let's continue with this solution. Now, looking at this, we have this is we have that 2x exponent y plus this equal to this. So the first thing we do is to cross multiply. When we cross multiply at this point, this is the x, so when we cross multiply, the x will now multiply this one. So we are going to have 2x exponent y, the x will multiply it, plus, because we are cross multiplying at this point, plus x squared exponent y plus cos y dy. Okay, so if you don't say you are cross multiplying, you can say multiply through by the x. Let's use that method so that we understand. So we say okay, let's call this equation 1. We say multiply equation 1 through by the x, and so we are going to multiply it through. So this one will be the x times into 2x exponent y plus the x times into x squared exponent y plus cos y dy over the x equal to 0 times the x. So we've gotten into this point. So we know that the x, okay, let me write it properly. So the x times this is going to give us 2x exponent y dx plus the x times all of this, we have the x here, so this will cancel out. And so we are going to have plus x squared exponent y plus cos y dy equal to, when we say 0 times the x, that will give us 0. Okay, so we've been able to have this multiplying the x and this multiplying the y, and it's equal to 0. So that brings us to this other equation, that m dx and dy equal to 0. So anyone that is multiplying the x becomes your m. So because we have m dx, it means our m equal to this, because the x is multiplying m. So we have, this will be exponent y, and our n, because whatsoever dy is multiplying becomes our n from this equation. So our n equal to x squared exponent y plus cos y. Now we are done with the first law. Now the second one, for you to say that this equation is exact because you have to test for the exactness of the equation before you can solve. It means you have to ensure that when you are differentiating m with respect to y and n with respect to x, that they are the same. So we can call this equation 2, we call this equation 3. So I'll say differentiating, let's say from equation 2, we are going to do partial derivative of m with respect to y, not with respect to x. So if we are differentiating m partially with respect to y, we are going to have 2x, because this is an exponent. So when we differentiate it, we have 1 times 2x exponent y. So this will give us the same thing, 2x exponent y. Now from equation 3, we are to differentiate n with respect to x partially. We are doing partial differentiation. So if we differentiate n with respect to x, we differentiate the n with respect to x, this is going to give us, because we are looking at x, we are differentiating n with respect to x. So this will give us 2. When we differentiate x squared, you have 2x, and you'll be left with exponent y. You'll not differentiate this one because you are not differentiating m with respect to y. You are differentiating it with respect to x. So this will be your answer. So if you call this equation 4, and you call this equation 5. Now if you look at it, partial derivative of m with respect to y is equal to 2x exponent y. And a partial derivative of m with respect to x is equal to 2x exponent y. So we can now make this mathematical statement. Since the m all over y equal to partial derivative of n with respect to x, and since this is equal to this, the equation is exact. And so since we've done that, since we've been able to establish that yes, this equation is exact, we can at this point solve the equation. It is at this point that we solve the equation. So in solving this equation, very simple. In solving this equation is going to be very simple. Note that in solving this equation, we are going to have that a function of x, y equal to a function of x comma y is equal to integral of m dx plus integral of n dy. So this is how to solve it, that integral of m dx plus integral of n dy. But actually, in actual sense, this is the formula. Now, but in order, if you look at it, if you look at it, this one is m dx, so it's considering only the values, it's integrating with respect to x, and this one is with respect to y. So in order to expand this, we have to expand this formula. We have to expand this formula to have it this way, that if into x comma y will be equal to integral of m dx plus integral of terms of n not containing integral of terms of n not containing x bracket dy, integral of terms of n not containing x dy. What does this imply? What it means is, if you have to take terms of n, we have what our n, this is our n, and this is our n. So if you have to consider, okay, let me just solve the equation. And so this is the same thing as saying integral of, right, integral of m dx plus integral of terms of n not containing x bracket dy. Note, n is multiplying the y and m is multiplying the x. So this will be equal to 0. This is equal to 0. So we have to implement this now. So this will be, what is our m? This is our m. This is the value of our m. Our value of our m is 2x exponent y. So I'm going to have integral of 2x exponent y dx plus integral of, we have been given a condition here, and the condition is terms of n not containing x. What this means is, these are terms of what? N. But anyone that doesn't contain x is what you use here. So if you look at these terms of n, x squared exponent y, it contains x, so you won't use it. So the only term of n that does not contain x is cos y. So we bring cos y here, so we are going to have cos y dy, so equal to 0. I have to explain this again. For this one, m dx, so you go to the value of m, this is m, and you just add the x to it. But in this second one, terms of n not containing x, it means these are the terms of n. But anyone that doesn't contain the value, the variable x, is what you choose. Okay? But if you look at this first one, it contains x squared, so you can't use it. But this one, cos y stands alone, there's no x attached to it, so that's the one you use. So we are done. So at this point, we can now integrate. Now, this one, you are integrating this one with respect to, note, you are integrating this with respect to x, not to y. You are integrating with respect to x, and this one you are integrating with respect to y. So when you integrate this, you are going to have, okay, since we are integrating with respect to x, let's bring out what we consider as the constant. So 2 and exponent y are the constants we have. So we have 2 exponent y. We bring it out and integrate only x dx, since we are integrating with respect to x, plus this one we are integrating with respect to y. So we have integral of cos y dy equal to 0. So we can now perform our integration now. So when we integrate x dx, we write our constant first, 2 exponent y. When we integrate x, it's going to be x. There's 1 here, original 1 here, so we have 1 plus 1, 1 plus 1, okay? 1 plus 1 divided by 1 plus 1, cos. When we integrate cos, when we integrate cos y, when you integrate cos y, you have sine y equal to, when you integrate a constant, you have, okay, you integrate this 0, you have c. So when you do this, you have 2 exponent y, x raised to power 1 plus 1 will be x squared divided by 2 plus, you have here sine y equal to c. And so you can cancel out here. This is 1 and this is 1. So you now have your this thing to be exponent y x squared plus sine y equal to c. Or you can choose to rewrite the equation this way to have that you bring x here so that you have x squared exponent y plus sine y equal to c. So basically this is how to solve an exact equation. Remember, you need to understand that for exact equation that m dx plus n dy will be equal to 0. And again, for you to solve an exact equation, you have to test for the exactness of that equation. And for you to test, you have to use this formula that the partial derivative of n for y must be equal to the partial derivative of n all over the partial derivative of x. And once you've been able to test for the exactness to ensure that the equation is exact, you can now solve. But there are situations, like I said earlier, that when you are tested, the equation would not be exact. You can use the method of integrating factor to convert the equation to an exact equation before you solve. So you watch out for my next video when I'm going to be solving that problem. Thank you.